Hybridization.
Hybridization.
Hey, what's up everybody?
JC and Claire are back!
This time we're gonna talk about ValenceBondTheory and hybridization.
To be specific about hybridization, we're talking about sp3, sp2, and sp hybridization.
Alright, let's get started. First of all, what is valence bond theory? Valence bond theory explains the bonding of two atoms that is caused by the overlapping of half-filled atomic orbitals. So instead of pinpointing the exact location of the electrons, we're going to map out the region of space in which the electron is more likely to spend its time.
And those regions of space are atomic orbitals s, p, d, f orbitals.
For example, dihydrogen monosulfide, or what we call hydrogen sulfide, with two hydrogens and one sulfur atom. For the hydrogen, the ground state electron configuration is going to be 1s, which is according to our periodic table. For sulfur, the ground state configuration is 1s2, 2s2, 2p8, 3s2, 3p4. So we're just gonna use the last two orbitals of sulfur and the 1s of hydrogen. So this is the electric configuration. So we have two half-filled 3p orbitals and one half-filled orbitals in both H. The 1s orbitals of hydrogen can combine with the 2p orbitals of sulfur. So they'll form a bond together. So this is the 3s orbital, which is fulfilled. The 3py, 3px, and 3pz. The 3px is fulfilled. Then, with two hydrogens, we're gonna combine two hydrogens. Then, it's going to be fulfilled because of the hybridization. So, let's move on to hybridization. Hybridization is the phenomenon of mixing up different orbitals of the same energy level of an atom to produce equal number of hybrid orbitals of same energy and identical properties. This is related to Sir Linus Pauling's statement that S and P orbitals can be combined mathematically. These orbitals, the hybrid orbitals, contain maximum two electrons with opposite spins. Focusing on our main subjects, sp3, sp2, and sp hybridization. But before that, we're gonna talk about some key terms. A sigma bond forms when two atomic orbitals overlap between these nuclei of atoms, known as the internuclear axis. On the other hand, a pi bond occurs when two atomic orbitals overlap outside the space between the nuclei. Outside the internuclear axis, the strongest bonds form with maximum overlap between orbitals. Atomic orbitals are the physical regions or space where an electron may be present or found, with a probability calculated from the precise mathematical form of the orbital. An sp3 hybridization has one s orbital and three d orbitals overlapping to produce four hybrid orbitals. Let's take methane for example. Its formula is CH4 with a configuration of 1s2, 2s2, 2p2. For hydrogen, 1s. So we'll just consider the 2s2 and 2p2 orbitals of the carbon for this moment. An sp3 hybridization, just what I said, has 1s orbital and 3p orbitals overlapping to produce four hybrids. So sp3 hybridization occurs when a carbon has four attached groups. Since those sp3 orbitals are only half-filled, each contains a single unpaired electron, which will then bond with the hydrogen. One sigma bond from the 2s of the carbon and 1s of hydrogen, and 3 sigma bonds from the 3p of the carbon and 1s of 3 hydrogens. Each will then have an angle of 109.5 degrees at tetrahedron. The S character would be 25% and the P character will then be 75%. An sp2 hybridization or trigonal hybridization requires 1s orbital and 3p orbitals to overlap and produce 3 hybrid orbitals. They are coplanar and directed towards the corner of an equilateral triangle. That's why it is termed as trigonal hybridization. Our next example is ethene, with a chemical formula of C2H4. it has 2 carbon atoms, that's why its prefix is in. Also, it has a double bond, that's why its suffix is in. But you will fully understand these naming conventions on our next video. Again, we'll just consider the 2s2 and 2p2 orbitals of carbon. Again, sp2 hybridization requires 1s orbital and 3p orbitals to overlap and produce 3 hybrid orbitals. Then there will be 1 anhybrid orbital. So, sp2 hybridization occurs when a carbon has 3 attached groups. Since there are 4p orbitals and only 3 are hybridized, 1 will remain unhybridized. Those 3 sp2 hybrids are only half-filled, which will then be available for bonding with hydrogen. There will be a total of 4 CH sigma bonds and 1 CC sigma bond and 1 CC pi bond for the interaction of unhybridized orbital. The angle formed is 120 degrees. The S character will be 33% and the P character will be 66%. An sp hybridization or diagonal hybridization requires 1 s orbital and 1 p orbital to overlap and produce 2 hybrid orbitals. This time, our example is acetylene or ethine with a chemical formula of C2H2. It has 2 carbon atoms and 2 hydrogen atoms. Considering again the 2s2 and 2p2 orbitals of carbon. Again, sp hybridization requires 1 s orbital and 1 p orbital to overlap and produce 2 hybrid orbitals. Sp hybridization occurs when a carbon has 2 attached groups. Similar to the other 2 hybridizations, there are only 2 sp hybrids and 2 unhybridized orbitals. Those 2 sp hybrids are only half-filled, which will then be open for bonding with hydrogen. There will be a total of 2 CH sigma bonds, 1 CC sigma bond, and 2 CC pi bonds made by the interaction of 2 unhybridized orbitals. The angle formed will be 180 degrees since it is going to be linear, with a 50% sp character. Thank you for watching!
Make sure to watch our next video about alkanes and cycloalkanes. Bye!
Hey, it's you! So did you like our video?
Make sure to hit that like button if you haven't subscribed to our channel yet.
Subscribe!